The next presentation in this session is from Ben McDonald. Ben's from the HP CHIUW development team, and Ben will present on removing temporary arrays in Arkouda.
Thanks, Josh. So hi, everybody. My name is Ben McDonald here at the CHIUW workshop, and I'm a software engineer on the CHIUW team. And this is the third Arkouda talk in a row, and I think the fifth on the day. So I apologize if the background is starting to sound a little too familiar. But I'm going to be talking about an effort to remove temporary arrays with a CHIUW Lisp interpreter in Arkouda. All right, so if you've never heard of Arkouda, which seems pretty unlikely at this point, Arkouda is a Python library that supports a key subset of the NumPy interface for data science. But Arkouda's value doesn't come from its interface, but its performance and scalability, which it achieves through a Python client that's using a CHIUW server in the background. And so a typical workflow that an Arkouda user might run through would be much like any other data science library like NumPy, except the user will likely be running on what's a much larger scale of data. And so an example of what this might look like in practice would be to read in hundreds of files, perform typical data science operations, and then evaluate those results as a data scientist. And the little note I've got here on the bottom of this slide is just pointing out that Arkouda commands are handled sequentially. Each one is ran separately and sent as a message to the server separately, unlike something like the DAS workflow, which allows queuing up of a bunch of different commands to all be run at once. And so to expand on that a little bit more and talk about the Arkouda model, I've got this little workflow diagram here that will run through some Arkouda commands and what's going on behind the scenes. And so in this initial setup code, we're allocating 2 Arkouda arrays. Each of these randint calls are sending a single message to the server, creating an Arkouda array, and sending back a pointer to that CHIUW array. And then finally, we're just creating a regular Python scalar value. And so from there, now that we've created our CHIUW or our Arkouda arrays, if we perform some data science in the form of a couple of binary operations on these arrays, like I mentioned on the last slide, each Arkouda command or function is actually going to make its own server call. So even though this like a times x plus y operation just looks like a single expression to the user, this is actually going to be making 2 server calls to the server. And the first one of those calls is for the multiplication and the second for the addition. And what this means is that we have 2 trips to the server from the client. And that adds some networking overhead. And also we have to store the result of that first multiplication as a temporary array. And that means that the memory footprint of the operation is going to be using more memory than you might have anticipated, thinking this was going to all be happening in place. And so in this next little code snippet here, you'll see that same problem illustrated, but on a larger expression. And so the more binary operations that are done, the more messages and temporary arrays are created, even though it all looks like one expression to the user and they might not understand the implications of what's going on there. And just to summarize here, so there are several messages and several temporary arrays created for a single expression in Arkouda today. So summarizing what we talked about on the last slide, commands are sent one at a time from the Python client to the CHIUW server, and each command is sent individually, even when it's written as a single expression. And so this model works well when you're doing complex, compute-intensive operations that are isolated from other code. An example of this would be something like a sort, where everything can be computed all at once, and it's a relatively expensive operation. And what this model isn't the best for is the case that I was illustrating on the last slide, where we're executing expressions or small blocks of code. And the reason that I've already highlighted is that Arkouda will take many steps to accomplish something that intuitively looks like it should be completed in a single step. And so the idea that was come up with to help remedy this use case where Arkouda could be doing better was to send those those expressions as a single message to the server to avoid those multiple messages and temporary arrays. And the idea here is that doing all of this at once could reduce memory usage, improve performance, and maybe enable some new features in Arkouda as well. And so the implementation for this effort came in the form of a Lisp interpreter. So if we look at this diagram here, this will show what's going on with the client side of the Lisp interpreter, where first we're taking the expression that the user's given us, in this case, that a times x plus y code. And then second, we create an AST and turn that AST into a Lisp expression. And then finally, we're going to send that Lisp expression to the server as a string and let the server handle that from there. And so now that our server has gotten a Lisp expression, the server first parses the expression, then evaluates the result, and then evaluates the result in place, and that's what's removing the need for the temporary arrays. And lastly, returns the result back to the client. And just to really highlight the impact of what this means, I brought back this old slide updated for the Lisp interpreter model. So the impact is just sending we're just sending just one message and creating 0 temporary arrays as compared to the standard Arkouda model. As compared to the standard Arkouda model, which is creating several messages and several temporary arrays based on the number of operations in the expression. So switching gears a little bit, looking at this from a user's perspective. So a user who wanted to use the Lisp interpreter in Arkouda would just need to add the Arkouda func decorator here, like in this code snippet, onto their function, which indicates to the client that the code should be converted to Lisp and sent as a single message. And what this means is that arbitrary Python code can be executed in a single message on the server side, not just binary operations like I've been showing here. So as long as parsing has been implemented for that new for any feature, arbitrary code blocks can be executed on the CHIUW side. And so what this means is we can now support new functionality, allowing users to write their own functions as server messages from the client side. We can reduce the memory footprint by cutting back on temporary array creation. And we can cut back on client to server communication. And we also have potential for improved performance, which I'll get into on the next slide. And so for the performance results that I'm going to be showing, I use that simple a times x plus y example that I've been using. And so if we look at the performance numbers here of our initial implementation, the Lisp interpreter code was about 100 times slower than standard Arkouda. So we were a bit off where we wanted to be. And I'll just mention briefly that a couple of sources of overhead that we identified were around dynamic expressions and algorithmic problems with the Lisp interpreter implementation itself. But luckily, we did have a chance to work on some of those overheads after seeing that 100x worse performance. And so the first optimization was the implementation of a memory pool that reduced the number of heap allocations made by the Lisp interpreter. And yeah, I see I'm running out of time here, so I will move on to the next optimization here. And so the next optimization was to chunk the array, parse the Lisp expression once per task. And this allowed so all the elements owned by the task could share the same parse expression, where previously we were parsing the Lisp expression for every single element in the array, which you can imagine would have a lot of overhead. And so now getting into the updated performance numbers here, we still had, there were some significant improvements for the Lisp interpreter, and we got about 50 times faster than that initial 0.29 gigabytes per second number. But we were still about 2x behind the standard Arkouda operations, unfortunately. And so in conclusion here, the Lisp interpreter is the start of a new evaluation model in Arkouda that can provide new functionality, reduce memory footprint, reduced memory footprint, and the performance is still around half that of the standard Arkouda model. And because of that, this is still a work in progress and something that myself and others have a lot of ideas for moving forward. And so we've identified where the majority of that overhead is coming from, and that is in the way that we've implemented the usage of generic types like integers and floating point values, having support for both of those, which doesn't play particularly well with, as opposed to Python's dynamic model with CHIUW's compiled model. And we haven't had a chance to address that yet, but we do have some ideas in mind for that yet. And then my last bullet point here is sort of the cliffhanger for all of you today, in that we ran some experiments on our Lisp interpreter to see what the theoretical upper bound performance would be. And we've seen that if we were able to optimize everything to perfection, the Lisp interpreter would be able to perform about twice the performance of standard Arkouda. So with any luck, that is what I'll be telling you all about next year. So that is all I had for my talk. Thank you. Are there any questions from anyone?
Thanks, Ben. Tom Westerhout has hand up. So Tom, do you want to ask a question?
Yeah, hi. So my question is, how could you comment a bit more about the implementation of the Lisp interpreter? Because initially I would think that you would require to JIT compile CHIUW, which is something new and very interesting.
Yeah, so we weren't doing like a just-in-time compilation or anything of CHIUW. What was going on there is, so we send that Lisp expression to the server as a string, and then we turn all of the symbols from that string, so like the A and the multiplication and everything, into tokens, and then we're going to generate like sort of like instructions to execute just in a loop. And so that's kind of what I mentioned, where we have to have we can support arbitrary code as long as we've implemented already. So like we had like hard coded in the multiplication and the addition handling of those tokens. So it's more of something that we've already compiled in rather than doing it on the fly or something like that. So it doesn't work with arbitrary blocks of code today, but only really binary operations today is the extent, but it could be extended more. Does that answer your question?
Yeah, thank you. Thank you.
I'm conscious we've reached the end of the time, so I'm just going to let people know that if you want to take a break, please do. I'm happy to stay here and watch questions. I know Brad has one now. Ben, hopefully you can stay to keep answering. Yeah. Okay, Brad.
Mine was less of a question for Ben, who I get to ask questions of pretty much all the time, and more kind of following up on Tom's comment. So Tom, since you sort of indicated maybe an interest in like, wouldn't it be cool if instead of Lisp interpreting an expression dynamically, there could be some sort of like JIT compilation? And that's definitely a model we've talked about as well, would be, what would it take to essentially create some code on the fly, compile it, link it into a running CHIUW application as a shared object or something like that. And I think long-term, we sort of imagine that to be something that the Dino compiler could potentially help with in terms of its ability to kind of both sort of stitch code together, create code in smaller chunks, as opposed to the whole program form that we use today. But even shorter term, I sort of feel like there might be something heroic one could do where you could create a shared object and sort of do the right things to get it loaded up. Of course, given that we're running distributed, it would sort of require loading it up across all of those CHIUW instances. So there are definite challenges there, but I think it would be an interesting pattern to explore, sort of doing by hook or by crook in CHIUW. And every time we talk about the Lisp interpreter and its overheads and trade-offs, in fact, you have to write Lisp code, which maybe isn't all that native or appealing to Python programmers who are using this. This is one of the other themes that comes up a lot. So I was just wanting to pass that along.
Yeah. Thanks. I think I might actually have a kind of a suggestion or a direction in that regard. So if, for example, if on the CHIUW side you could say that you receive some arbitrary function that you then map over local parts of the array, such that the JIT compilation only needs to happen on a specific locale. And there are quite a few libraries available that kind of let you generate highly efficient code benefiting from SIMD and stuff, and they can also generate GPU kernels as well.
Okay, using what input languages?
So one such library would be, for example, Halite, that's kind of embedded in C++. But you could easily kind of imagine kind of calling out to that library from Chapel as if it were just an external dependency. And then what that library basically does, it builds the AST for you, and then you call a function and it compiles it down to via LLVM, it compiles it down to machine code. So if that data that you're manipulating is rather big, which I would imagine would be the case for Arkouda, the overhead of JIT compiling should be kind of negligible.
Okay, great. Thanks for those thoughts and pointers.
Ben, I actually had a question if you got time. I think you were moving towards this with the idea of decorating particular Arkouda operations as Arkouda funcs. Do you think it might be necessary to fully support this model to distinguish between the kinds of Arkouda operations that just transform the data set versus the kind that actually provide some externally visible result to the user, like writing something out to a file or returning something to the client? Other programming models like Spark have this distinction between those two different kinds of operations. Is that something that the Arkouda client user needs to know about, or do you think we can get away with the approach that you've described so far?
So you're saying, like, rather than having the Arkouda func decorator having to require that users have that, we would instead just like know intuitively which expression should use that and which should not? Is that what you're getting at, or?
It's actually more the other way around. Like, do you think a data scientist using Arkouda needs to recognize that distinction and think about it when they're writing their workflows?
Yeah, that's an interesting question. I mean, to be honest, I have to say that the client side, I kind of just got something working, and that hasn't. I spent more time on the Chapel side of things. So the model as we have it today, where the user has to specify the Arkouda func, like I think I understand what you're saying. Like, that's a little bit more knowledge than we'd like to have to require the users to have of what's going on behind the scenes. And I honestly don't have the best answer to that question, but I think it's something interesting to think about, is like how we can best expose that to the users and what we want that interface to look like. And so you mentioned that Spark is a good example of this usage. I definitely would like to look into that if that's what you'd recommend.
Yeah, I think they call the kind of functions, the Arkouda funcs that you're developing, I think they call them transformations in Spark. The idea being that, yeah, you can chain them together and fuse them and so on without creating temporary objects necessarily. Yeah.
Okay, thank you. Yeah, I'll definitely look into it. Yeah.
Yeah, thanks.